Patterns in mathematics. Math helps us find patterns all around us, from the shapes in nature to the things we see at home and even in the stars in the sky. We use patterns every day. When we go shopping, cook with our family, or play games with friends, patterns are always there to help us. Finding patterns can feel like solving a fun puzzle. That's why mathematicians see math as both an art and a science. Patterns help us understand the world better. They can help us solve problems, create new things, and make our lives easier. Patterns in the stars helped us learn how to travel to space, and patterns in our DNA help doctors find cures for diseases. Math is everywhere, and patterns are waiting to be discovered. Let's explore them together and see what new things we can find. Thanks for watching. Remember to keep an eye out for patterns all around you. Patterns in mathematics. Just like there are patterns in nature and art, there are also patterns in numbers. Mathematicians study these patterns to understand how numbers work. This field of study is called number theory. Number sequences are some of the most basic patterns in math. A number sequence is just a list of numbers that follow a certain rule. Let's explore some interesting number sequences. Did you know that many number sequences can be visualized using pictures? Visualizing mathematical objects through pictures or diagrams can be a powerful way to understand patterns and concepts in math. Our first pattern is very simple. It's called the all ones pattern because every number in this sequence is the number 1. Next, we have the counting numbers 1, 2, 3, 4, 5, and so on. These are the numbers we use to count things every day. Now let's look at odd and even numbers. Odd numbers are like 1, 3, 5, and so on, while even numbers are 2, 4, 6, and so on. Can you spot the difference? Even numbers. These are numbers that can be evenly divided into 2 equal groups without any leftovers. For example, if you have 6 apples, you can divide them into 2 groups of 3 apples each, without any apples left over. Because they can be evenly paired, they are called even numbers. Odd numbers. These are numbers that cannot be evenly divided into 2 equal groups. For example, if you have 5 apples and try to divide them equally into 2 groups, 1 apple will be left out. Because there is always an odd one out, these numbers are called odd numbers. Triangular numbers are numbers like 1, 3, 6, 10, and so on. When you arrange them as dots, they form a triangle. Square numbers are numbers like 1, 4, 9, which can make perfect squares. Cube numbers, like 1, 8, and 27, can be stacked to form cubes. A square number, also known as a perfect square, is a number that can be expressed as the product of an integer multiplied by itself. The name square comes from the geometric shape of a square. If you arrange balls in a grid to form a square, the total number of dots will be a square number. Visually, these numbers form perfect squares, hence the term square numbers. A cube number, or perfect cube, is a number that can be expressed as an integer multiplied by itself twice. The name cube comes from the 3-dimensional geometric shape of a cube. If you arrange balls to form a cube, the total number of balls will be a cube number. Visually, these numbers form perfect cubes, hence the term cube numbers. There are many more interesting number patterns. Let's try to visualize one by one. Virahonka numbers. These numbers follow a unique pattern. Each number is the sum of the 2 numbers before it. We start with 1 and 2, then 1 plus 2 equals 3. Next, 2 plus 3 gives us 5. After that, 3 plus 5 equals 8, and the pattern continues. Virahanka, a mathematician from ancient India, discovered this pattern over 1,000 years ago. Amazingly, we can see Virahanka numbers in many places around us, in the number of petals on flowers, in the spirals of pine cones, and even in beautiful art and music. Virahanka number is also known as Fibonacci numbers. Let's explore the exciting world of powers of 2. These numbers follow a simple pattern. Each number is twice or double the one before it. We start with 1, then double it to get 2, then double 2 to get 4, and the pattern goes on. 8, 16, 32, 64. Powers of 2 are really important in our everyday lives. If you've ever played a doubling game, you've seen how fast things can grow when we keep multiplying by 2. Let's explore the powers of 3. Imagine starting with the number 1. When we multiply by 3, we get 3. Multiply by 3 again, and we get 9. Then 27, 81, and the pattern continues. Each time, the number gets 3 times bigger. Powers of 3 show up in many places like math puzzles, games, and even in patterns we see around us. It's amazing how numbers grow so fast when we keep multiplying by 3. Now that you know some number patterns, try to find patterns in the world around you. Have fun discovering your own number patterns. Thanks for watching. Keep exploring math and finding patterns everywhere you go. Welcome to our journey of discovering patterns in numbers. Today, we will explore some amazing ways to visualize the relationship among the number sequences which we have learnt in the previous video. Let's dive in and see the beauty of math unfold before our eyes. Let's explore the patterns while adding odd and even numbers, which we have already discussed in the previous video. When we add 2 odd numbers together, like 3 and 5, the sum is an even number, 8. Why does this happen? It's because an odd number always has one leftover dot, and when we add 2 odd numbers, these 2 leftover dots combine to make another pair, resulting in an even total. When we add an odd number and an even number, like 3 and 4, the result is an odd number, 7. This happens because the even number already makes perfect pairs, and the odd number adds 1 extra dot that doesn't have a pair, so the total remains odd. Finally, when we add 2 even numbers like 4 and 6, we always get an even number, 10. This is because both even numbers are already perfectly paired, so when you add them together, they still form complete pairs, resulting in an even sum. So remember, adding 2 odd numbers gives an even result because the leftover parts pair up. Adding an odd and an even number gives an odd result because there is always 1 extra dot. And adding 2 even numbers gives an even result because all dots are perfectly paired. Let's start with a fun question. What happens when we add up odd numbers? Let's see. 1 equals 1. If we add 3 to 1, we get 4, and that's a square number. Then 1 plus 3 plus 5 gives us 9, another square number. Similarly, 1 plus 3 plus 5 plus 7 gives us 16, which is another square number, and so on. This keeps happening, and it's such a beautiful pattern. But why does this happen, and will it continue forever? Let's find out by using pictures. Because this works for any size of the square, we can see why adding odd numbers always gives us square numbers. Can you figure out the sum of the first 10 odd numbers? Yes, the sum of first 10 odd numbers is 100. Can you see some pattern emerging? Sum of first 1 odd number is 1. Sum of first 2 odd numbers is 4. Sum of first 3 odd numbers is 9. Sum of first 4 odd numbers is 16, and so on. Finally, we have seen that the sum of first 10 odd numbers is 100. Can you generalize this pattern for first n odd numbers? Yes, it is n square. The sum of first n odd numbers is always n square. When we add up counting numbers like 1, 1 plus 2, 1 plus 2 plus 3, we can imagine it as a growing triangle. Each new row adds more dots to form a bigger triangle. For example, 1 plus 2 equals 3. 1 plus 2 plus 3 equals 6. 1 plus 2 plus 3 plus 4 equals 10. 1 plus 2 plus 3 plus 4 plus 5 equals 15, and so on. Here's another cool pattern. We can also create square numbers by adding numbers up and down, like 1, 2, 3, and then back down to 1. For example, 1 plus 2 plus 1 equals 4, which is 2 square. 1 plus 2 plus 3 plus 2 plus 1 equals 9, which is 3 square. 1 plus 2 plus 3 plus 4 plus 3 plus 2 plus 1 equals 16, which is 4 square. 1 plus 2 plus 3 plus 4 plus 5 plus 4 plus 3 plus 2 plus 1 equals 25, which is 5 square. This pattern continues. When we count the numbers up and down, the sums are 1, 4, 9, 16, and these are square numbers too. When we add counting numbers up and then down, we create a pyramid shape. Each layer of dots represents a number in the sequence. The pyramid forms a square shape, explaining why this sum gives us a square number. If we continue this pattern up to 100 and back down, we form a giant pyramid. The base of the pyramid has 100 dots, and we know that this pattern will always create a square number. When we add any pair of triangular numbers like 1 plus 3, 3 plus 6, 6 plus 10, and so on, they fit together to make square numbers. For example, 1 plus 3 equals 4, which is 2 square. 3 plus 6 equals 9, which is 3 square. 6 plus 10 equals 16, which is 4 square, and so on. Let's explore centered hexagonal numbers. These numbers are a special type of hexagonal numbers with a dot right in the center. Imagine starting with 1 dot in the middle, then 6 dots are added around it, making 7 dots total. To find the next centered hexagonal number, we add another ring of dots around the hexagon, giving us 19 dots. Is it possible to create hexagonal numbers from triangular numbers? Let's explore it. When we multiply triangular numbers by 6 and add 1, we form a hexagonal number. It's like fitting triangles together to make a hexagon. For example, here we multiply the triangular number 6 by 6 and then add 1. This will give us 37, which is an hexagonal number. Did you know that when you add centered hexagonal numbers, you get cube numbers? Let's see how that works. The first few centered hexagonal numbers are 1, 7, 19, 37, and so on. When we add these hexagonal numbers together, something surprising happens. They add up to cube numbers. For example, if we take the first hexagonal number, which is 1, and then add the next one, 7, we get 1 plus 7 equals 8, which is 2 times 2 times 2, or 2 cubed. If we keep going, adding 19 to 8 gives us 27, which is 3 times 3 times 3, or 3 cubed. Adding the next hexagonal number, 37, to 27 gives us 64, which is 4 times 4 times 4, or 4 cubed. When we add powers of 2 numbers, like 1 plus 2, 1 plus 2 plus 4, 1 plus 2 plus 4 plus 8, and so on, and then we add a 1 to the sum, we create numbers like 4, 8, 16, and so on. It is amazing to see that these are the next power of 2 number. Now it's your turn. Look for patterns among different sequences. Use pictures or diagrams to find new ways numbers connect and relate to each other. Remember, math is so much fun when we look for patterns. Try finding other sequences and visualize them. Share what you discover with your friends and family. Who knows, you might uncover a brand new pattern. Thank you for watching. Keep exploring the wonderful world of numbers. Stay curious, keep learning, and most importantly, have fun with math. See you next time. Hello, young mathematicians. Today we will explore another fascinating aspect of mathematics, patterns of shapes. Just like number sequences, shape sequences have rules and patterns that mathematicians love to study. Let's dive in and discover the amazing world of shapes. We can observe such patterns in 1 dimension, or 2 dimension, or 3 dimension, or even in higher dimensions. The branch of mathematics where we study shapes and their patterns is called geometry. Here we have a series of shapes called regular polygons. A polygon is a flat shape with straight sides. When we say regular polygon, it means all sides of the shape are of equal length and all its angles are equal too. We will study more above angles in the upcoming videos. Let's look at these polygons one by one. The first shape is a regular triangle, also known as an equilateral triangle, with 3 sides. Next, we have a square, a regular quadrilateral with 4 sides. The shape with 5 sides is a regular pentagon. With 6 sides, we have a regular hexagon. The shape with 7 sides is a regular heptagon. The octagon has 8 sides. The nonagon has 9 sides. The decagon with 10 sides comes next. And finally, we have an hendecagon with 11 sides. Notice how the number of sides of these polygons increases by counting numbers 3, 4, 5, 6, 7, and so on. This pattern continues, and you can keep adding sides infinitely. Here, for example, we jump to a polygon with 100 sides, called a hectagon. This shows a fascinating relationship between shapes and numbers. The number of sides of these regular polygons follows the sequence of counting numbers, linking geometry and arithmetic together in a beautiful way. Here we can see a series of complete graphs. A complete graph is a shape in which every point, or vertex, is connected to every other point by a line. We start with the complete graph for 2 points, called K2. Here we have just one line connecting the 2 points. Next we have K3, the complete graph with 3 points. Every point connects to every other point, forming a triangle with 3 lines. Then we move to K4 with 4 points. Here, every point connects to all 3 other points, giving us 6 lines. For K5, we have 5 points, with each point connected to 4 others. This results in 10 lines. Finally, we have K6 with 6 points. Each point is connected to 5 others, creating 15 lines in total. If you look closely, you'll notice a pattern. The number of lines in each complete graph corresponds to the triangular number sequence: 1, 3, 6, 10, 15, and so on. This is because, in a complete graph, each new point connects to all the previous points, adding lines in a way that mirrors how triangular numbers are formed. So, complete graphs offer a great visual way to understand triangular numbers. Now here we can see a series of shapes called stacked squares. Each shape is made up of smaller squares arranged into a larger square. Let's start with the first shape. It has just one small square. Next, we have a shape with 4 small squares arranged into a 2 by 2 square. Then, we have 9 small squares arranged into a 3 by 3 square, followed by 16 small squares in a 4 by 4 square. Finally, we have 25 small squares arranged in a 5 by 5 square. If you observe carefully, each of these shapes represents a square number. A square number is the result of multiplying a number by itself. For example, 1 square is 1 times 1. 4 squares are 2 times 2. 9 squares are 3 times 3. 16 squares are 4 times 4. And 25 squares are 5 times 5. So when we stack these small squares to form bigger squares, we can visually see how square numbers grow. Each time, the number of squares increases in a way that matches the pattern of square numbers: 1, 4, 9, 16, 25, and so on. This visual pattern helps us understand the concept of square numbers in a fun and engaging way. Let's explore this interesting arrangement of stacked triangles. We start with a single small triangle. In the next step, we add 3 more triangles directly beneath it. Then, we add 5 more triangles in the third step, and 7 in the fourth, and so on. If we observe closely, the number of triangles added in each new row follows an odd number pattern: 1, 3, 5, 7, and so on. But here is something even more fascinating. The total number of triangles in each complete shape follows a square number pattern. When we have 1 row, we have 1 triangle. With 2 rows, we have a total of 4 triangles. With 3 rows, the total is 9 triangles. And with 4 rows, the total becomes 16 triangles. The numbers 1, 4, 9, 16 are all perfect squares. This happens because as we add each new row of triangles in increasing odd numbers, the overall shape forms a larger triangle that grows both wider and taller, forming a perfect square pattern in terms of the total count of triangles. So what we're seeing is how adding triangles in an odd number sequence creates shapes whose total number of triangles matches the square numbers. It's a wonderful example of how patterns in mathematics can reveal surprising connections. Let's take a look at the Koch snowflake, a fascinating example of a fractal in mathematics. The Koch snowflake begins with a simple equilateral triangle, which is our starting shape for iteration n equals 0. This triangle has 3 sides. At each subsequent step, or iteration, a new smaller triangle is added to the middle of every existing side. For example, in iteration n equals 1, each of the 3 sides of the original triangle is divided into 3 equal parts, and an equilateral triangle is added in the middle of each side. This step gives us a shape with 12 sides. In iteration n equals 2, the same process is repeated on all 12 sides of the shape. Again, each side is divided into 3 parts, and an equilateral triangle is added to the middle of each segment, resulting in a total of 48 sides. As we continue this process, the number of sides increases dramatically. At iteration n equals 3, we now have 192 sides, and by iteration n equals 4, the number of sides grows to 768. If we observe closely, the number of sides follows a specific arithmetic pattern. Mathematically, we can express the number of sides at each step as 3 times 4 raised to the power of the iteration number, n. For example, at n equals 1, we have 3 times 4 to the power of 1, which equals 12 sides. At n equals 2, we have 3 times 4 to the power of 2, which equals 48 sides, and so on. The Koch snowflake is a remarkable shape because, as we continue to add smaller and smaller triangles, the perimeter of the shape increases infinitely, but the area remains finite. This illustrates the beautiful and often counterintuitive nature of fractals, where simple rules and patterns can create complex and infinite forms. Patterns are everywhere. From the sequences of numbers to the shapes we see, patterns reveal the hidden beauty of mathematics in our daily lives. By exploring number sequences and their connections to geometric shapes, we uncover fascinating relationships and surprising discoveries. Thank you for joining us on this journey through the world of patterns in mathematics. We began by exploring patterns in numbers and number sequences, and then we looked at how these sequences relate to patterns in shapes. We hope this exploration has inspired you to keep finding and learning about patterns around you. Who knows what amazing patterns you'll discover next? Thanks for watching, and keep discovering the magic of mathematics.